All right, today we're going to introduce a topic from chapter 16, acids and bases. And this will be the material for exam 8. And then the last chapter we're going to cover after this one is chapter 18, redox reactions. And that will be essentially the final exam. That will be the material covered on the exam given during final week. Right? There's no comprehensive final. It's just that on during final week, you'll have an exam on chapter 18. So this is the next to the last chapter. Acids and bases. All right, there are not too many topics to cover here. So we're going to take our time and make sure we get every topic thoroughly examined. Before we get into the acid-base topics, there needs to be some introductory material that I give you on equilibrium. And all of this material is found in chapter 17. Only the discussion that we have today on the material from chapter 17, only this material will be part of the next exam. Anything else in chapter 17 that you want to study, that's fine, but you're only responsible for the slides that I show you here on chapter 17. And the reason that I've introduced this part of chapter 17 into chapter 16 discussion is because acid bases are better understood if we have a basic understanding of equilibrium. So here goes. Equilibrium is an expression we use in chemistry and physics, referring to two opposing processes. If those processes if we see, and our example here is evaporation and condensation. So if we have a flask that's filled with some liquid here, and we're evaporating some of those molecules into the air, into the space here. We have to have a stopper in it. When we first stopper that flask, the molecules start to evaporate and go from liquid to gas. Now we're not talking about chemical equilibrium yet. This is purely physical to give you a handle on what equilibrium means. So when these molecules exit the liquid phase and go into the vapor phase, that's evaporation. Initially, since there are no molecules up here in this space, there's no way for them to return, right? There's nothing up there, so there's no return. But eventually, you get enough of these up here that you start to see a condensation process, a return. Okay? Now, on the macroscopic view, what we actually see happen is that the level of this liquid will gradually decrease. And it will decrease to a point where it stops decreasing. At that point, we say the system is in equilibrium. Evaporation and condensation are now balanced. But on the microscopic level, what's actually happening with the molecules themselves, the activity is occurring at a furious pace. In other words, evaporation and condensation are now occurring at exactly the same rate. So you get so much going into vapor phase, same amounts coming back. That's why you don't see any change in the level of the liquid. So the microscopic view or understanding explains the macroscopic observations. Okay, and this only occurs if that's stoppered. So you can build up a concentration of molecules up here. Now they have the opportunity to return. If you pull that stopper out, then the volume available to the vapor is infinite. And it'll eventually keep evaporating until it's all gone. You can't set up an equilibrium that way. It has to be enclosed. Okay, so that's the concept of equilibrium. Two processes, this direction, that direction, are occurring at exactly the same rate. When that happens, you have equilibrium. And this is referred to as a dynamic state. That is, something's actually happening, even though we don't observe a change. That's dynamic versus static. Static is where nothing actually does change. It's all static at any level of observation. Dynamic simply means that the rates are balanced. Okay, now let's take this concept and transfer it into an understanding of chemical equilibrium. Chemical equilibrium, as you know, would be based upon a chemical reaction. And we know how to write a chemical reaction. We have reactants, right? Add reactants on this side, and then you have products on this side, okay? The way we represent a chemical equilibrium is to give it a reverse arrow. So you have an arrow going this way, an arrow going that way. Chemical equilibrium refers to a reaction in which the reactants produce products. And then as we produce products, now the products can return. They can become reactants in the return reaction. So now we have a balance between the forward reaction and the reverse reaction. And if those rates are exactly equal, then we have a state of chemical equilibrium. All right. Now, the actual concentrations of reactants and products will vary depending on the particular reaction we're investigating. Some reactions will produce almost all products and very little reactants left. And other reactions will have mostly reactants and just a little bit of product. Okay, so there's a lot of variability in there, depending on the reaction that we're studying. And it all has to do with balanced rates. Now, there was a Frenchman back in the early 19th century, I believe, who took this concept of chemical equilibrium and took it one step further. If a system like this is in equilibrium, it has established equilibrium. We have some reactant, some product, and the rates forward and the rates reverse are equal. Once that equilibrium is established, then it is possible to disturb the equilibrium, to do some kind of a change that will force the reaction to respond. That's at the heart of Le Chatelier's principle is, if this is equilibrium and we do something to it, say we add some of this component, this product, what will the reaction do? It will respond in such a way as to reestablish equilibrium. So how does it do that? If we add C, then it's going to have more C available to react with any of the D's that are there. So those encounters are going to produce a reverse reaction. So this rate increases until we reestablish a balance. We produce some more of these, and now we get a balance again. So what we're saying is that any system in equilibrium if it is disturbed, will respond in such a way as to reestablish equilibrium. Here's an example. So if we have water, vapor, okay, gas phase, and carbon monoxide, and this is in equilibrium with hydrogen gas and carbon dioxide, then we know that the forward and the reverse rates are equal. Now, let's say what would happen if we add more water vapor? So we add more of this. What's going to happen? How does this concentration affect the equilibrium? Well, since we've increased the number of molecules of water, now you have more interaction, more possible reactions between any carbon monoxide that's in the vessel and the added water. So now you get an increased rate in this direction until you build up some more of the products, and now their reverse reaction again balances it. Okay. What if we add more hydrogen? If we add more hydrogen, we get an increase in the reverse rate until we build up enough original reactants so that their rate now balances. Okay, so the reaction will shift to the left until we reestablish equilibrium. Okay. So there is a way to quantify equilibrium in chemistry, and it's called the law of mass action. So if we have, that's good. If we have this reaction, these are our coefficients. We have a balanced equation. Okay. At any given temperature, as long as the temperature is constant, then we can write an expression for this reaction in terms of the concentrations of each of the reactants and products. And this value will always be constant for that given temperature. It doesn't matter what concentration. You get a high concentration here and a low concentration here, or you could have an even lower one here and not so high here, or you could have a high here and a low there. Those values can be different for every situation. But when we put them into this expression, they will be equal to a constant value. And the way we express that concentration is usually in molarity. Remember, molarity equals moles per liter, right? Moles per volume. This is moles per liter. Okay? And that's typically how we express the concentrations. So we take the products, the concentration of C at equilibrium, when we don't see any more changes, and raise it to the power of its coefficient, times concentration of D raised to its power. And then we put the product, the reactants, in the denominator with their powers. Okay? That's an equilibrium constant. And it's constant for a given temperature. If you change the temperature, then you will change the value of the constant. Okay, here's an example. If we react nitrogen and hydrogen, this is my favorite reaction. This is the Haber-Bosch process. To make ammonia. Okay. The expression then would be, what is the concentration here? And by the way, these are all gases. So we've studied molarity in terms of solutions, concentration of a solute in a solvent. But gases can also be expressed in terms of molarity if you have a confined volume. Say you have a container that is exactly 1 liter, and you put a mole of your gas into that container. It's going to fill the whole space, and the concentration will be 1 mole per liter, or 1 molar. So we can do this for gases as well as solutions. So the K for this one would be ammonia concentration to the 2nd power divided by nitrogen concentration to the 1st power, and then hydrogen concentration cubed. That would be your equilibrium expression for the constant for this reaction. And the reaction must be as written, it must be balanced before you can write this expression. Now, this is an equilibrium constant. I'm going to draw a distinction between equilibrium constant and equilibrium position. Okay. There's a difference. Equilibrium constant is exactly what it says. It's constant. Any values you put in here from an equilibrium determination will give you a constant value every time for that temperature. Equilibrium position, though, considers the absolute concentrations of all the reactants and products. So if this system is at equilibrium and we add more hydrogen, then we will shift the equilibrium to the right, and some of that hydrogen will be used up, but not all of it, only enough to reestablish equilibrium. So the value of concentration of hydrogen now is different. And we used up some more nitrogen, so its concentration is different. And this concentration is different. That is a change in equilibrium position. But if we take those different values, plug them in here, we get the same constant. So the equilibrium position can vary, but the constant cannot at a given temperature. All right. So let's see, what do we have here? We have this equilibrium equation. What's the equilibrium constant expression? Right now, this is an acid right here. That's acetic acid, right? And we're going to talk about that a little more in just a minute. And one of these hydrogens right here, this hydrogen broke away. So now it's off by itself. And what's left is this anion. So this is known as an acid dissociation equation. All right, so let's write that up here as the acid is in equilibrium with that cation and this anion. All right. Now, these are all in aqueous solution, dissolved in water. All right. So we can write an expression here for their equilibrium. We would put the concentration of hydrogen ions, concentration of, right? That's the acetate. polyatomic ion. You'll find it in that list that I gave you earlier when we were naming these compounds. That's the acetate. And then in the denominator, we have the reactants. Concentration. So when you first put this into water, there's none of this in there. None to speak of. None of these originating from that molecule. But eventually, there is a dissociation. Some of this leaves and produces these products, and now they can go backwards and forwards. And once that equilibrium is established, this will be the constant for a given temperature. So that's the best expression for this acid dissociation. And very often, you'll see different subscripts for the K's, right? If it's just an equilibrium expression, you'll see a KEQ. If it's one like this, you may see A in there for acid dissociation. Okay? And there are several others that I'm not going to bother you with right now. Okay, for this reaction, now we're going to use actual numbers and see what the value is for a given reaction. In this case, we've got one reactant and one product. We have dinitrogen tetroxide. That's a gas. And it dissociates into two molecules of nitrogen dioxide. Okay, so the K for this expression would be NO2 squared divided by N2O4. Okay, and we're given values here. These values were determined at equilibrium. So N2O4 is 0.055 molar. Okay. And NO2 is given as 0.060 molar. Okay, and it's squared. And if we do that calculation, we should get 0.065, 0.065 as the constant at this temperature. One thing you'll notice is I didn't put molar in here, I didn't put molar in here, and there are no units for this. There are units, but as convention, we don't write the units for equilibrium constants. The reason for that is sky's the limit, right? You can have molarity squared divided by molarity, which would be molarity, right? But suppose this one is squared and this one is to the 5th power. Then you would have a different, like molarity to the 3rd power. Or you could have combinations. You could have, since there are powers here and there are multiple multipliers in the numerator and denominator for different reactions, this could very quickly become unwieldy. So by convention, we don't write the units here, which means that we have to be extra careful. We have to be meticulous about the way we do the calculation so that we don't make mistakes. Because now, since we don't have the units to guide us, then we can't check our work based upon the units of measure like we typically would do. And if you go to a reference manual and look up the value for the K for any given reaction at a given temperature, there will be no units. It will simply say units derived from molarity. Right? That table would be all those reported values would have been derived from original molarity concentrations. And there are other options. If they're all gases like this, we could use partial pressure. Right? Okay, we could do that. In that case, there would be a different set of values. They would not be the same numbers. But the point is that the reference manual will only reference the origin of the concentrations, whether it's molarity, partial pressure, or other possibilities. And then it won't list any units for the actual calculated values. All right. So that's one example. We've calculated the equilibrium constant for this reaction, given that data. All right. Okay. What can this K value that we've calculated tell us about the reaction? If the K for a reaction is, let's see, let's write up our generic reaction here. Right, we've calculated a K for that value. Right, so we have C and D divided by A and B. Okay, we calculated a value for that. Now, if the equilibrium as established gives us a value of K that's very, very small, much less than 1. If this value is extremely small, what does that tell us about the reaction, the equilibrium position for a set of concentrations? What it tells us, since this is in the numerator and this is in the denominator, that means this term is very small relative to this term. That is, the reaction prefers reactants, right? If it's much less than 1. If the value is much greater than 1, then it prefers products. All right, that's what that's saying. Now the slide implies that if it's exactly equal to 1, it's perfectly balanced, concentrations on both sides. But we can't say that because of these powers. Right? Those powers will influence the value. But if we can say something about very much smaller than 1 or very much larger than 1, then we can say something reasonable about the position. Right? And since that value will change with temperature, the temperature could influence the reactions in such a way that they could flip. The K could actually change from a large one to a small one with a temperature change, or from a small one to a large one. And so that's why the temperature has to be constant for the K to be valid. All right. Let's see, I've said all those things already. Oh, one other point. If we are given a K here, and we're given values for any of these, and say this one is unknown, it's like any algebraic expression. If you've got an equation with one unknown, you can solve for it. So if you know the K, and you know the equilibrium concentrations for the rest of them, you can solve for the unknown one. All right. So if the equilibrium lies to the right, the value of K is very large. Okay, if the equilibrium lies to the left, then the value should be very small. All right. Okay, now that we've got those basics of equilibrium in hand, we can apply them to a study of acids and bases. So we're back into chapter 16 now. All right, concepts of acids and bases. The first concept of a scientific nature that was proposed was by a man named Arrhenius. And Arrhenius' concept of acids and bases was that the molecules that are put into solution either have hydrogens that can dissociate, such as our acetic acid earlier, and we write a generic like this. Right? There's your hydrogen that can dissociate, and it can produce hydrogen ions and whatever's left over. Arrhenius also said that bases will follow a similar process, only now we have some part of the molecule and a hydroxyl group. And this would produce that plus that. Okay. That was Arrhenius' concept. The molecules must have hydrogens for acids, hydroxyls for bases. All right. The problem is there were some solutions that could be made that produced basic character. They have hydroxyls in solution, but the molecule does not have hydroxyls in it. Perfect example. If we put ammonia in aqueous solution, it will produce hydroxyls. So where did they come from? They didn't come from the ammonia molecule because there's nothing there. So we have to introduce another concept. And we eventually discovered that the ammonia was reacting with water molecules. Water was becoming an active participant in the reaction. So what was happening was a proton was being transferred, a hydrogen atom, a proton, a positive charge, one of these, was being transferred to that molecule. And it was producing the ammonium ion. Well, when you do that, right, when you take one of these away and give it to ammonia, what's left behind? Well, you're leaving the electron behind because the positive's going here, so the electron is going there. So you got two electrons here, and you have an imbalance of 1 minus charge. That's where the hydroxyl was coming from. Okay, so we need a new concept. And that was proposed independently by two researchers. Lowry was in Britain, Bronsted, I think, was in Sweden. So they came up with the same idea virtually at the same time. And they were going to base their definition of acids and bases on proton transfer, hydrogen ions, H+. Why do I keep calling it a proton? Because hydrogen has one proton, and most hydrogens only have that one proton. So if you lose an electron, then what's left? A positive charge, a proton. That's it, because there was a proton and electron. One electron out here in orbit. So if this one's gone, you're left with a proton. So that's why hydrogen ions, I call them protons. All right, so Bronsted and Lowry proposed this definition. An acid is any molecule in aqueous solution that can donate a proton. So there you are. This acid can donate a proton. There it is. It donates that proton to something else. And a base is anything that can accept a proton. So let's say we have a base here of any kind. If we can add a proton to it, then this is a base. It accepts a proton. This would be a base, hydroxyl, right? Hydroxyl plus hydrogen ion. This is a base that accepts a proton and produces water. We're going to talk about that in just a minute, but in more detail. Okay, those are the two basic concepts for acids and bases in aqueous solutions. Right. There's another way to express acids and bases, but we're not going to cover it in this class because it's used primarily for non-aqueous environments. But we're staying in the aqueous world, in the water world. And these are the two most commonly used acid-base definitions. Okay. So this brings us to another point. The way we wrote the acid dissociation here, like that and that, that never happens. Right? I wrote it as if it does happen. What does happen is the proton is transferred to something else. And that's why we write it in this way. For that particular example, hydrochloric acid is in aqueous solution. Right? So we transfer a proton here, and now we get a polyatomic ion called the hydronium. And what's left is chloride ions. Okay, that's what actually happens when an acid is placed in aqueous solution. Protons are transferred from the acid to the water molecule. So what that makes this is an acid, and this is a base, according to Bronsted and Lowry. This is the donor. This donates a proton. This accepts a proton. Okay. So this is typically what happens to an acid when you put it in aqueous solution. It transfers a proton. Now, for calculation purposes, this works just fine. Right? But I just wanted to make the point. This is not what happens in the solution. This is what happens. But we can use this expression to do our calculations to get an understanding of what's happening. As long as we realize that that proton is not free floating. Okay. Protons are only transferred. They're not independent agents. All right. By way of definition, if this is an acid and this is a base, now on this side, this species, this hydronium ion, is able to donate a proton, which makes it an acid. But it's related to this base. So we call it the conjugate acid. This is the conjugate acid of that base. That means that with this acid producing this species, this is now a base. that theoretically can accept a proton. So this is the conjugate base of that acid. Okay. And this sets up in an equilibrium, right? For this example, this equilibrium lays way to the right. So its K value would be almost infinity. So notice that for this acid, the conjugate base has the same term here and here. The only thing that's missing is one proton. And that always happens. When you are looking for a conjugate acid-base pair, you look for this term is the same on both sides, and it can be anything. It can be C2H3O2. It can be acetate. Right? We could write it like this. This is our acid. If it loses a proton, it produces that conjugate base. So this is an acid-base pair. This is the same on both sides, and this is missing from that side. One proton at a time. All right. So this just emphasizes the movement of the proton from the acid donor to the water acceptor, which makes it a base. All right. So which of these following are actual acid-base pairs? All right. Let's see. HCl, HNO3. Let's do them one at a time. I'll write them all up here first. Okay. So they're saying, is this an acid-base pair? Next one, H3O plus and OH minus, and H2SO4, and SO4 2 minus, and HCN and CN minus. Okay. What's wrong with this picture? That is different from that. Besides, this is still an acid. It didn't accept a proton from this side. It didn't lose a proton to give you, right? So that one can't be an acid-base pair. How about this one? What would happen to this one if it lost a proton? Right? It has a proton here. What's left over? Water. So this would be the acid. This would be the conjugate base. Right? That's not the conjugate base of this acid. Right? So that one's wrong. How about this one? Well, this is similar here, SO4, but it lost 2 protons in the process. You can't do that. Not for an acid-base pair, only 1 proton at a time. So this reaction would be like that. 1 proton, what's left over? HSO4 minus. That would be the conjugate base. So this one's wrong. How about this one? There it is. This is the same here. We lost a proton to get to there. This one, that one is an acid-base pair. A conjugate acid-base pair. Now, I will say, if we take this one, it can also transfer that proton. So if we did this one, HSO4 minus, and it lost a proton, and notice I'm using an abbreviated form here. I'm not drawing the hydronium ion. Right? This is the abbreviated form, which I've told you earlier, this is not what happens, but it does explain the situation as long as we recognize that this is transferred to a water molecule. All right, so, and this would be SO4 2 minus. So for this one to be correct, it would have to be that and that. That would be correct based on this reaction. But as it is, D is the only correct answer for the problem as presented. All right. Now, let's talk about acid strength in chemical terms. We all have an idea and intuition about dangerous acids, right? You know, well, maybe you don't know, because now lead acid batteries that service your automobile's engine have within them concentrated sulfuric acid, H2SO4. Right? And it's very dangerous. Used to be, they couldn't seal them because they would produce dangerous concentrations of hydrogen gas and you could get an explosion. So they were always vented. And by venting the battery, you lose water over time. And that's why we used to have to check our batteries to be sure the fluid level was correct and replenish it. But now the technology has developed so we can seal the batteries and make them safer, both against explosions and against corrosive attack against metals and your skin or your eyes or breathing the fumes, whatever. But that corrosivity is not an expression of acid strength. Acid strength in chemical terms refers to an acid. A strong acid refers to one which is completely ionized, completely dissociated. So this one would be a better example. That one produces these two species, and this part is almost completely gone. We can essentially say that this is completely to the right. Right? So this will be in the numerator. This would be in the denominator. Right, K. And this is, for all intents and purposes, 0. So remember math class, what is the, when you calculate anything divided by 0, what do you get? Infinity, right? So the K value for this one is pretty close to an infinite. Okay, that is a strong acid. And the definition of a strong acid is one which is almost or completely dissociated. Right? The hydrogen ions transferred to water, and what's left over, the conjugate base, is in solution. All right. For this example, we're transferring a proton to water, and the reaction is essentially all to the right. On the other hand, a weak acid is the converse. In other words, for this one, right? For this one lies Let's change this. This one lies very far to the left. In other words, only a little bit dissociates. And this scenario lies in the realm of equilibrium expressions, equilibrium constants. Because as long as you have some of this and some of that and some of that, then you can calculate a valid K. It doesn't have to go to infinity, or it doesn't have to be zero. Right? This would not be, this part of the expression would not be zero. It would be a small number, but that's the definition of a weak acid. It's only partially dissociated. Most of the acid molecule remains intact, in solution. Far to the left. Okay, so the top diagram here refers to a strong acid, where you essentially produce hydrogen and conjugate base, and that's it. That's all that's left in solution. Where a weak acid, you still have some of the acid plus a tiny amount, relative to which acid it is, of protons and conjugate base. Now, what we want to do is try to draw some conclusions about strong acids and weak acids. If we have a strong acid, well, let's put this one up here again. This one produces essentially those two. So here's the conjugate base of this acid. Think about it logically. If this acid is very eager to dissociate that proton, get rid of it, what would be the character of the conjugate base? Does it want the proton back? No, it doesn't. So for a strong acid, like hydrochloric acid, we always produce a weak conjugate base. And the stronger the acid, the weaker the conjugate base. So if we have a weak acid like this one, what's the nature of its conjugate base? This is a strong conjugate base. Right? They work just opposite from one another. All right. Okay. For a strong acid, the forward reaction is dominant. For a weak acid, the reverse reaction is dominant. And if the acid is strong, then the conjugate base is weak. And if the acid is weak, the conjugate base is strong. There it is. That's out of your textbook, that table. And that's what it means. So these are some common strong acids. In chemical terms, right? Sulfuric acid. Right? So this one would produce that plus this. Like that. That would be strong. Strong acid, weak base. Okay. Now, I don't know if I have a slide on it in here, but I'm going to say it now because it's stream of consciousness. The strong acid character of sulfuric acid is due to its first proton. If we try to remove a second proton, this becomes a weak acid. And the way to rationalize that is you're trying to separate a proton from an already negative acid. And it's more difficult, right? There's an attraction between the negative and the positive, so it's more difficult to remove that second one. This one is a weak acid, that one's a strong acid, right? So the character, the strength character of sulfuric acid comes from its first proton. Of course, hydrochloric acid, it's only got one proton, so it's a strong acid. Nitric acid is a strong acid. Perchloric acid is extremely strong and dangerous. Not just for its the acid strength, but for its ability to oxidize organic matter, right? Even if it wasn't a strong acid, it would still effectively oxidize your skin on contact. All right, so remember the nomenclature. Remember, we don't call HNO3 hydronitric because it has an oxygen in it. We don't start with hydro. We only start with hydro if there's no oxygen present. Remember that from nomenclature. So it's just nitric acid. All right. Let's see. Those are just reminders that we studied when we were naming acids earlier. Now, here's another characteristic of acids. If we have an oxyacid, in other words, any acid that has oxygen to which a hydrogen is associated. Right, so sulfuric acid would be S, and then we have 4 O's. Right? And then this is a double bond, that's a double bond. This one has a hydrogen, and this one has a hydrogen. So it's H2SO4. This is an oxyacid because these hydrogens would have to dissociate from contact with an oxygen. We can do the same thing for acetic acid. Right? Let's see. Carbon, we have hydrogens here. Right? Those 3 hydrogens here. Then we have this carbon. And this carbon has 2 oxygens attached to it. One of them is a carbonyl, or double bonded oxygen, and the other one has the hydrogen. This is the one that is responsible for that. Okay? This is also an oxyacid. And there are other examples there on the slide. All right. What other types of acids do we have? Well, organic acids, and acetic acid is an organic acid. An organic acid has a carbon atom backbone. In our case, it was 2 carbons hooked together with the acetate ion. And commonly, but not always, you will have this group here responsible for the acidic character. This is the carboxyl group. And they're called carboxylic acids. There are a whole host of them. They're not the only ones. And I'm going to show you one that's not carboxylic acid, but it is organic. Right? We just have to scroll down through them. There's acetic acid, right? And written that way, this shows you which hydrogen is attached to which carbon. Right? So that's one way of writing it, rather than the typical way that we've written it before. Right? They're exactly the same. They're just, the structures are written differently. Okay, how about this one? Lactic acid. Anybody who's ever exercised after a sedentary period where your muscles get weak, and you want to strengthen them up, anybody who has exercised knows lactic acid. Lactic acid is the product that's produced in your muscles after you exercise them, and it makes them sore. Formic acid. Formic acid is a carboxylic acid like acetic acid here. Only the atom attached to this carbon is not another carbon, it's a hydrogen. So this is not the hydrogen that's acidic. That is the hydrogen that's acidic. And formic acid gets its name from the family name for ants. They are, the Latin is, I can't remember the Latin name, form, F-O-R-M, is Latin for ant, or formus, whatever the case may be. So that's why when we find formic acid in ant bites, particularly fire ants. If you've ever encountered a fire ant, then you'll know what formic acid feels like. All right, those are all carboxylic acids. Citric acid is also, only citric acid has three. There's one, there's another one, there's another one. The way the molecule is written in convention for organic chemicals is wherever you have two lines coming together, right here, here, and here, those are carbon atoms. Okay, it's more convenient just to write where the lines come together. If there's nothing there, it's a carbon. If there's not, if you want it to be something else, then you actually write in what it is, like here, oxygens, hydrogens. There's that's a carbon, and there are two hydrogens there also, and two hydrogens here. Okay. Don't worry about that. The point here is the carboxylic acid nature of citric acid. It has three of them, three carboxyl groups. And then the last one is a non-carboxyl acid, uric acid. There's the structure for uric acid. And the it has several acidic hydrogens on it. Probably the most acidic hydrogen is this one, because it sits between these two oxygens, and we don't have time to go into that right now, but that's probably the first hydrogen that dissociates to make an acid. And then the second one would be one of these right here, or maybe even this one, I don't know. But the these are organic acids. Uric acid, right? Anybody who's got gout knows uric acid. It collects in your joints. Or if you've if a bird has flown over and pooped on you, right? It's got brown and white mixed together. The white part is uric acid. Uric acid is a solid. And that's the way birds get rid of their excess nitrogen from protein and nucleic acid metabolism, is because it doesn't expel water, right? They conserve water and they conserve weight. Whereas humans, we get rid of our nitrogens by another molecule called urea. Right? But that's soluble in water. We have to expel water when we get rid of urea. There's some all fish and some reptiles get rid of their excess nitrogen as ammonia. Right? There's also a toxicity factor. Ammonia is very toxic in small concentrations. So fish and those reptiles, amphibians, they have to expel ammonia continuously. They don't collect it in a bladder. Whereas we can collect urea in a bladder and expel it when it's convenient, because it's not as toxic. And then uric acid is even less so. toxic toward the birds and some reptiles. Okay, that's a side note. The point here is acids come in all sorts of different varieties, and they all have one thing in common. They give up a proton in aqueous solution. Okay, so now let's talk about concentrations of acids and do some calculations. Right? So we have a 1 molar solution of hydrochloric acid, and we want to order these things in order of strongest to weakest base. Okay. So if we have 1 molar HCl, what is its conjugate base? Well, it's going to produce this plus this. Right? So this is a strong acid. This is a very, very weak base. Okay. Right. Chloride is a very weak base, right? Very weak. So if we're going to put it in order of strongest to weakest, the weakest base would be to the right. It would be this, right here. That would be the weakest base out of that group. All right. If HA is a weak acid, then it's going to produce that plus a very strong base. So it'll be over here. All right. And water's caught in the middle. How well does it accept protons? Well, not very well, actually, but it accepts protons more readily than A- would. So that's the order: A- water, chloride ion for this problem. Now let's take it one step further. Let's say we have 2 acids, acetic acid and hydrocyanic acid, I believe. Yeah, they're both weak acids, but this is a stronger acid than this one. So if this one's a stronger acid than that one, then this should be a stronger base than this one. Right? And this is not greater in concentration. This is strength. That's what that means. Okay. So arrange these bases from weakest to strongest. Right. We're going to talk about it on the next slide. We have cyanide ion, acetate ion, we have chloride ion, and we have water. We want to arrange those in order of weakest to strongest. Okay. Again, let's see. That's a partial explanation. I'll get to it in just a second. The weakest is going to be this one because it comes from the strong acid. So we know that this one, see, from weakest to strongest. Oh. From weakest to strongest. The strongest is going to be the weakest acid. This one. So now it becomes a toss-up between these two. So when we express water, and we've thrown something at you here that I probably should have come later, but we'll get through it. In pure water, one water molecule can react with another molecule of water and set up an equilibrium. So if we consider this one as the donor and this one as the acceptor of the proton, then we get this acid donor produces that conjugate base. And this conjugate acid. Okay. It just so happens that the K value for this reaction, we give it a KW, is equal to 1 times 10 to the minus 14. So it's very much in this direction, only produces a slight amount of these two conjugates. So that makes this one, since this is a very, very small number, and in fact, we didn't give you a value for this one or for that one, but we did say that this one would be a weaker base than that one. But the relationships, how does this one compare to that one? Well, as it turns out, weakest to strongest. You know what? That might be backwards. Because this one is K value about 10 to the minus 5. And this one's about 10 to the minus 10, something like that. No, it's even bigger than that. I think this one is like 10 to the minus 15. Anyway, what that means is this is a very, very strong base. And I think this K compared to that K should put water here. Oh, excuse me. No, we're not talking about this one. We're talking about that one. Okay. All right, let me back up. Regardless of what these are, the trick here is that we're not talking about this conjugate base, which would be extremely strong. We're talking about the water. So the water has an affinity for protons that produces a very strong base. So this one would be in excess of this one as a base. That's why water must come here and acetate has to come here. All right. Okay. So let's get back to this discussion of water. Let's make some room here. And let's just start over again. How about that? So we've got H2O plus H2O produces hydronium in aqueous solution and hydroxyl in aqueous solution. All right. This is known, this behavior of any compound, in this case water, is called amphoteric. That means both. Ampho means both in Greek. Ampho means that it can go both ways. It can be an acid or a base. And this works for water, but it works for other things too. We could use ammonia here. Pure ammonia, what they call anhydrous ammonia. And it would also do one of these. Okay. Its amphoteric nature means that it can go both directions. But it's more important for us to study water because we're talking about aqueous solutions. So in this case, we're calling this an acid. and this a base. That makes this a conjugate acid and conjugate base. Okay, and the KW here is expressed in terms of this one times that one. Now, why didn't we put these in here? We only want these. Because by convention, solids, pure solids, and pure liquids are not included in equilibrium expressions. So these are liquids, they're gone. They're not even in the denominator. So this KW is only this concentration times that concentration because they are in aqueous solution, but these are not. The reason we do that is because these concentrations don't change, right? It's like, what's the concentration of me in myself? It doesn't change. If you want to think of it that way, you can think of these concentrations as incorporated in that value. But that's convention. Solids and pure liquids are not included in the equilibrium expression. So when we do this, we come up with a value of 1.0 times 10 to the minus 14 at 25 degrees C. All right. Now, one very, very important point to make here. When we are studying acids or bases in aqueous solutions, the acid dissociates, the base accepts a proton, but this reaction is always there. It never goes away. The question is it significant compared to the other reactions you're studying? That's the question. So don't forget that this reaction in aqueous solution is always there, no matter what else we do. Okay. So we have three general situations in aqueous solutions. One in which this concentration, and we can write it this way also, comes out with the same number. Okay. The situation where this concentration is exactly equal to this concentration, that's called a neutral solution. Okay. If those are equal, then it's neutral, right? So what does that mean? If it's pure water and you have this value and these are equal, what concentrations do you have here? 10 to the minus 7, 10 to the minus 7 molar. That's neutral. How do I know that? Because 10 to the minus 7 times 10 to the minus 7 is 10 to the minus 14. Right? You just add the exponents. I know that for a neutral solution. Okay. If the hydrogen ion concentration is bigger, is larger than the hydroxyl, then you have an acidic solution. The imbalance is toward the protons. So, for example, if this one, instead of 10 to the minus 7 now, is 10 to the minus 6, right? That's a bigger concentration than this one, isn't it? By a factor of 10. What does this one have to be? Well, you have to multiply this one times this one to get that one. So this one has to be 10 to the minus 8 molar. Okay, and there you have it. This one is bigger than that one. If we go the other direction, where the hydroxyl is greater than the hydrogen ion, say this one's 10 to the minus 6. This one has to be 10 to the minus 8. Now you have a basic. This is neutral. This is acidic. And this is basic. And there are other examples, right? If this one gets bigger and bigger, 10 to the minus 5, 10 to the minus 4, 10 to the minus 3, then this one has to get smaller proportionately based upon that relationship. Okay? In each case, it's always hydrogen ions times hydroxyl ion concentrations equals that value. Always. So in an acidic solution, which of the following statements is correct? Well, let's see. For an acidic solution, hydrogen ions less than 10 to the minus 7? No, that would be basic, wouldn't it? Hydrogen ions greater than 10 to the minus 7? Yeah, B is correct. Okay. How about hydroxyls greater than 10 to the minus 7? No, that would be basic. Hydrogen ions less than hydroxyls, that would also be basic, right? So the only one that's true is B. Okay. All right. Let's try an example here. I'll leave that there for reference. And we'll just make room up here. In an aqueous solution in which hydroxyl ion concentration is 2 times 10 to the minus 10. Hydroxyl concentration is 2 times 10 to the minus 10 molar. The hydrogen ion concentration is how much? Well, we know this and we know this. We can solve for that. Let's not. I was going to skip a step. Let's do it like this. That concentration here equals this. Right? So hydrogen ion concentration would be equal to 1 times 10 to the minus 14 divided by 2 times 10 to the minus 10. Okay. We could use our calculator, but I'm going to try to do it without my calculator. So this part of the mark is 1/2, 0.5. And this part is 10 to the minus 4. Correct? Yeah. This minus 10 is subtracted from this minus 14, which makes it a plus 10. It's minus 4. Okay, so let's do 5 times 10 to the minus 5 molar. Because I moved this one to the right, I stored up that negative decimal in here. So 5 times 10 to the minus 5 should be, okay, it's either C or D, right? 10 to the minus 5 means that it's greater than 10 to the minus 7, which makes it acidic. That makes C the correct answer. Oh, we're going to do calculations. There you go. And there you go. And there's again, hydrogen ions greater than hydroxyl, the solution is acidic. There you go. All right, now, everything we've done so far is true. We've discussed equilibrium and the concentrations in terms of molarity. We've discussed acidity and basicity and calculating the K values and expressing, solving problems for hydrogen ion concentration, hydroxyl ion concentration in terms of molarity. But these values are always very small. They always have exponents. And they can get to be unwieldy. And if you're doing this type of work day in and day out, you want something a little more convenient. And that's where Sorensen came in. I'm not sure if I got his name yet. Sorensen. I think he was Swedish, might have been Danish, Scandinavian anyway. He was working with hydrogen ion concentrations in solutions, and he wanted a system that would allow the expression of these acid concentrations in simpler form. So he created this mathematical transformation of the data. He called it pH. So there's your hydrogen ion, and there's whatever. All he did was he took the logarithm of the hydrogen ion concentrations, and since the hydrogen ion concentrations always have a negative exponent, like, well, 10 to the minus 7 molar, right? So what's the log of that? Remember your logarithms, right? This is base 10. The logarithm of that is the power of 10 that equals that value, right? What's the power of 10 that equals that value? The power of 10 is minus 7, right? So the log of this one is minus 7. But he didn't want to work with negative numbers either. So he just stuck a negative out here. Change the sign. There you go. So the pH of 10 to the minus 7 molar hydrogen ion concentration is 7. So if you have this, the pH is going to be 7. All right. Now notice that as the concentration increases, right, if we go from 10 to the minus 6, 10 to the minus 6 molar, then the pH is equal to 6. This is more hydrogen ions than that one is, right? So as we increase the molarity of hydrogen ions, increase the acidity, the pH decreases, right? Because we put this negative number out front. So as this increases, pH decreases. So the more acidic the solution, the lower the pH. Now, how do we deal with significant figures? All right. The number of decimal places in the log, and this is from mathematics, the number of decimal places in the logarithm that is derived is equal to the number of significant figures in the original number. So if we say significant figures here is 2, right? Then when we convert that to pH, we should use 2 decimal places, right? And when we convert back to this one, we can only have 2 decimal places in our coefficient. Okay. So the significant figures in the molarity number is the same number of decimal places in the pH. All right, so what does this mean? Well, we discovered that this was neutral before, because this will be the same concentration in aqueous solution as the hydroxyls. That would be neutral. So neutrality is pH 7. That's neutral. All right. Let's make room here. Or maybe I've got a scale. pH greater than 7 is basic, and pH less than 7 is acidic. All right, here's some examples. Right, pH 7, there you see in the middle is pure water. Blood is slightly basic. right? If you've had anatomy and physiology, then you probably know that the normal pH range for blood is 7.35 to 7.45. I believe that's right. And we're going to talk about that as our last topic. This is the topic of buffers. How does your blood stay within that range with everything that's going on? And that's where buffering comes in. But hold that thought. We'll talk about it later. Okay, so anything that's a lower pH is acidic, like vinegar. Vinegar is in the neighborhood of a little over 3. Lemon juice is less than that. Stomach acid is between 1 and 2. Right? If you eat a big tomatoey Italian dinner, right, your stomach pH may drop to 1. In which case you might need a couple of Tums. And then 1 molar hydrochloric acid is pH 0. Isn't that odd? How can you have a pH of 0? Actually, you can have a pH negative. It's simply because this expression is purely mathematical. Whatever the concentration is, do the calculation, and the pH comes out as a valid mathematical calculation. Now, it's not very useful, right? pH is down that low. pH less than 1 is not very useful. And Sorensen didn't intend to use it there either. His pH range was typically between 1 and 12. So if we go the other direction, right, past blood, household ammonia is in the neighborhood almost 12 pH. And then 1 molar sodium hydroxide is 14. All right, so that gives you an intuition about pH and acidity and basicity. So let's calculate the pH for each of these solutions. What do we need to know to calculate the pH? We need to know the hydrogen ion concentration. So for the first one, that's easy. It's given to us. Times 10 to the minus 4, right? Molarity. So pH is equal to negative log of 1 times 10 to the minus 4, right? What's the power that gives you this value? Minus 4. So this is minus 4 times a minus equals 4. And we've got 2 significant figures, so it should be that. So that's the first one. There you go. I should have put 2 decimals there for the significant figures. Oops. So how do we get this one? We're given hydroxyl ion concentration here, 0.040 molar hydroxyl. How do you get hydrogen ions out of this? Well, remember our equation. Kw equals 1 times 10 to the minus 14, which is equal to hydrogen ions times hydroxyl ions. And so we know hydroxyl, we just put 0.040 in here and solve for this one. So 1 times 10 to the minus 14 divided by 0.04 is equal to 2.5 times 10 to the minus 13 molar. Now all we have to do is take the negative log. So the negative log of 2.5 times 10 to the minus 13 equals what? I take the log of that, change the sign. So round it off. Let's see. pH, 2 significant figures. So we get 12 2 decimal places, 60 pH. By the way, if you write it like this, it's wrong. Or if you write it like this, it's wrong. Or if you write it like this, it's wrong. This is pH, not those other three. Okay, so let's see. Got some animation here. Here we go. There we go. Calculate your hydrogen ion concentration. And then take the negative log of that. And you get 12.60. All righty. The pH of a solution is 5.85. What's its hydrogen ion concentration? So now we're going to go backwards. How do you do that? It's easier than it sounds. So we've got a pH of 5.85. What does that mean? That's equal to the negative log of hydrogen ion concentration. Okay? Well, what does a log mean? A log, this is base 10. This is the power of 10 that equals that, except that we got a negative there. Right? So you got to get that negative over here. All right, now 10 to this power equals that. There you go. So let's see, let's punch it in the calculator. 5.85, change the sign, and then your calculator will have a key in it, 10 to the X. There'll be a log key here, and then there'll be above it. So you'll have to say, all right, if I'm going to use this key for that, I got to hit the shift or the function key. And if we do that, let's see, there's mine. We get 1.41 times, let's see, 2 decimals, 2 significant figures. 1.4 times 10 to the minus 6. Molar. Here we go. And I added an extra one there. That's not right. This is correct based on our rules for significant figures. Okay. Now I'll throw another curve at you. pH is a mathematical calculation. That's it. Negative log of hydrogen ion concentration. What if we do the same thing with OH? Let's call it POH. Negative log of hydroxyl ion concentration. How about that? That's perfectly valid. All right. Here's another one. Suppose we have KW. We can do pKW. That's the negative log of KW. Okay, that's perfectly valid. What's the expression though for KW? KW equals hydrogen ions times hydroxyl ions. And that's equal to 1.0 times 10 to the minus 14. Okay? So what if we do this negative log thing to the entire equation? This would be pKW This would be pH. This would be POH, right? And what do you do when you take the log of X times Y? That's the same thing as saying the log of X plus the log of Y. So that means this is a plus. Okay. Now let's take the negative log of this one. That's 14. Okay. Now, let's see, I think that's animated. Animated. Yeah. Okay. And there we go. All right. So this expression is a little easier to deal with, right? Remember when we had OH hydroxyl ion concentration? I think it was 0.040 molar. We could convert that to POH and put it in this formula and calculate pH and get our 12.61. There it is. Okay. So let's use that formula. And what is the POH for each of the following? So 1 times 10 to the minus 4 is hydrogen ion concentration. Correct? pH then would be equal to 4. So POH is equal to 14 minus 4. And that's equal to 10. POH for the first one. There you go. There you go. There you go. And there you go. 10. So what's the POH for this one? 0.040 molar hydroxyl. So the negative log of 0.040 equals 0.040. Change the sign. And that's 1.40. POH. So what would the pH be? That's not the problem, but if we wanted to know the pH, we could say 14 minus 1.40, which is equal to 12.6. Okay. There we go. So that's the same answer we got before when we were looking for pH. How about this one? What's a solution is 5.85. What's the POH? All right. I'm going to just animate this one. So 5.85 subtracted from 14 gives you POH of 8.15. And then you take the anti-log of the negative. Anti-log of negative 8.15 to give you OH concentration. 7.08 times 10 to the minus 9. Okay. So what if we have given to us the concentration of a strong acid? In this case, in the interest of time, since we're getting short on time, we have a hydrogen ion concentration of 2 molar HCl. Right? That dissociates by this reaction to hydrogen ions and chloride ions. So what's the concentration of hydrogen ions in this case? is 2 molar, right? There you go. Now calculate the pH. Negative log of 2 is minus 0.30. There it is. There's a minus pH. Because this is purely mathematical. This is a calculation, pure and simple. Like I said before, Sorensen wasn't interested in these very low pHs. He was in the middle range. They were more valuable to him. And there, he was studying proteins, and proteins never got that low in pH. In fact, if you try to measure these pHs we're calculating, you can measure them with a special meter. It has a probe that you put in your solution, and the probe generates an electrical signal that is interpreted by the meter as a pH. But those meters don't work very well below 2.5 or greater than 10.5. You need a special electrode for those. Okay, how about this one? An aqueous solution of 2 times 10 to the minus third hydrochloric. So what's the hydrogen ion concentration? The only reason the hydrogen ion concentration is the same as the hydrogen chloride is that the ratio is 1 to 1. And then we calculate the pH, right? And we get 2.70. So this is definitely an acidic solution. All right, here's a curve. Suppose your hydrogen, you added hydrochloric acid in this concentration, 1.5 times 10 to the minus 11 molar. Okay, how do you calculate that pH? Well, here's where you need to consider water. Right, this is from hydrochloric acid. How about from water? Neutral water. What's the hydrogen ion concentration? 1 times 10 to the minus 7 molar. Okay? So what impact is this going to have on that? Nothing. This one is 10,000 times larger than this one. This will have absolutely no impact on the pH. So the pH would be 7.0 still. Okay, that's why you have to consider the concentration or the factors around the amphoteric nature of water. Okay, there you go. So the pH would still be 7. How about this one? HNO3. All right, there you have. What does this one do in water? It's a strong acid, so it's going to produce this plus this. And if this concentration is 1.50 times 10 to the minus, oops, my mistake, 2 molar. What's this concentration? 1.5 times 10 to the minus 2 molar. Right. So we can calculate the pH of this solution. 10 to the minus 2 molar is 5 orders of magnitude larger than water would produce, 10 to the minus 7. Right? An order of magnitude is a power of 10. So 10 to the minus 2 is 5 would be 100,000. No, yeah, 100,000 times larger than 10 to the minus 7. Right? So we don't have to consider water. We just calculate the pH for that concentration of nitric acid, 1.82. Very, very low concentration. That, in fact, is corrosive by EPA and OSHA. EPA and OSHA standards. Anything less than 2.5 is considered corrosive. Anything greater than, actually it's less than 2, is corrosive, or greater than 10.5 is corrosive as a base. So that is a corrosive solution. It's dangerous. Oh, by the way, before we get into buffers, we talked about strong acids and weak acids. Okay. This is a weak acid by chemical terms. All right, it's a weak acid. That's acetic acid. It's very weak. In fact, 5% acidity solution of this is what you have in a bottle of vinegar. Right, so it's perfectly safe at that concentration. But I used to use this acid in the laboratory, and it would come in bottles where it was 100% pure. They called it glacial. %. Nothing in there but acetic acid. That is extremely dangerous. It's a weak acid, yes, but it's so concentrated that it produces hydrogen ion concentrations that are off the scale. They're very high. It is extremely corrosive. Not only that, this is an organic compound. Right? If you put it in the neighborhood of an oxidizing acid or any oxidizer like sulfuric acid, put that together with this, it will explode. Right? So beware, if you're ever in a laboratory where you have concentrated acetic acid, you want to keep it away from sulfuric acid, nitric acid, perchloric acid, any of those types of acids. Keep it away from those. Otherwise, you will have an extremely exothermic reaction. Just a safety note there. Okay, now let's talk about buffers. What is a buffer? In chemical terms, we refer to a buffer as any solution that resists a change in its pH if we try to disturb its equilibrium by adding an acid or a base. Okay? That is a buffered solution. A buffered solution is in equilibrium until you add an acid or a base to it, and then it shifts to mitigate that disturbance according to Le Chatelier's principle. And buffers are very good at it within a range of pH that's designed into the buffer. You have to choose your buffer correctly, and it will maintain a pH that's very close to its equilibrium point, whether you add an acid or a base. So the question is, how does it do that? Well, typically, most buffers are composed of weak acid and its conjugate base. Right? A certain amount of this and a certain amount of that. Let's see if I got it animated here. Yeah, there's a weak acid and its conjugate base are in solution at the same time. So you mix it that way. You make it that way. So how does it resist a change in pH? Well, if you add acid, let's say here, like that. If you add acid to the solution, you're adding protons, right? So what's it going to do? It's going to consume protons and move to this side. So if pH is equal to the negative log of hydrogen ion concentration, then what's going to happen to the pH? If you consume most of the protons that you add, then the pH is not going to shift that much. Now, it won't be rock solid. It will change a little bit, but it won't change much. What happens if you add hydroxyl? Right? If you add hydrogen ions, you shift that way. If you add hydroxyls, right, they're going to add here and produce water. Right? And then what will happen? Well, if you're removing hydrogen ions by this reaction. So what's the response? The reaction will move to that side to replace them. Not all, but most of them. So that again means that the hydrogen ion concentration doesn't shift very much. Okay? So that's what happens to the added hydrogens. They react with this strong base and they're consumed. If you add hydroxyls, then the hydroxyls pull off these hydrogen ions and shift it that direction. And that's what we're trying to show in this reaction. Okay. That is 99% of the buffers. There are other possibilities for buffers. We can use ammonia, which is a base. And that's on this slide. We can make a buffer out of ammonia. So how would we do that? There's your acid, there's your base, right? So how did it get here? Well, like that. So if we add acid, acid is going to react with this ammonia and make ammonium. Or if we add base, the base is going to remove this, right? And then this is going to shift back that way to replace them. So you get a similar reaction. So, okay, if a solution is buffered with ammonia, which has added ammonium chloride, there you go. So there's your ammonium and there's your ammonia together. What reaction will occur if a strong base, such as sodium hydroxide, is added? Sodium hydroxide will consume protons from this one, or on this side, whichever the case may be, right? So ammonium chloride is a strong electrolyte that dissolves to form ammonium. There you go. Chloride ion is a spectator, right? It's a very, very weak base. It's perfectly happy just like it is. So it's not going to do anything. Right? So you get the ammonia is the conjugate acid of ammonia. Ammonium is the conjugate acid of ammonia, and it will react with strong base to form the conjugate base ammonia. Right? So the best answer is B. You get it reacting sodium hydroxide, which is this part right here. It transfers a proton there. Right? So this makes water, and what's left over? There you go. Okay. All right. That's the last slide. So you've got PowerPoint slides in Brightspace. You've got a review document in Brightspace and worked problems to go along with it. You also have practice tests that you can do in Brightspace on this chapter that can give you that can drill you in these types of problems. And then you have your homework. So by next Tuesday, we'll take that review document and we'll work some more problems. And if you show up for the Zoom lab, you can ask me questions. If you show up on Zoom, you can ask me questions. If not, then you can just watch the video and